So our last talk for this morning's session is titled Towards Compositionality and Video Understanding by Roei Herzig, Amir Globerson, and Trevor Darrell.
Hi, everyone, and thank you for joining me today. I'm Roei. I'm a PhD student at Tel Aviv University and a visiting scholar at Berkeley AI Research Lab. I'm working with Professor Amir Globerson, Professor Trevor Darrell, and my research goal is to develop compositionality into intelligent machines to improve robustness and generalization. And as the title suggests, I will focus primarily on the video understanding aspect today. So we will present today a bunch of our work in collaboration with many collaborators from Tel Aviv University, IBM Research, Reichman University, and UC Berkeley. But I would like specifically mention Elad Ben Avraham, a master's student from our group, who has been a key contributor to this work. So in recent years, deep learning has revolutionized different fields, dramatically improving applications such as visual recognition, content synthesis, autonomous driving, and generative AI. Huawei, current technology is still far from human skills. The large gap stems from the fact that human reasoning uses a high-level semantic understanding and common sense, while deep learning models do not fully capture them. And one possible solution might be found in compositionality, but what is it exactly, compositionality? So the key aspect behind compositionality is that humans understand the world as a sum of its parts. For example, the human perceive the color blue, they know how an elephant looks like, and thus they can easily recognize a blue elephant. Our understanding of the world is naturally hierarchical and structured, and when new concepts are introduced, humans tend to decompose the familiar parts to reason over what they do not know. And this leads to the hypothesis that intelligent machines would need to develop a compositional understanding. And it seems today that many existing vision architectures are not compositional. For example, even training large vision language models over 5 billion images and textual descriptions does not yield improved results on understanding objects, attributes, and their relations. Furthermore, we still do not know what architectures help models learn compositionality and how to refine the balance between compositional and black box models. And I am personally motivated by these questions, and I hope to convince you today that compositionality is an interesting topic. So compositionality is a key aspect of video understanding. Videos are composed of actions, and they are performed by the objects, which create long-range spatial-temporal dependencies. Different compositions would lead to a different outcome. Specifically, it is because the temporal domain differs from the spatial domain in two crucial aspects, causality and sparsity. For example, if we are looking at a video of somebody making a tasty omelet, we see the eggs, seasoning, interaction with some ingredient, and in the end of the day, you will get a tasty omelet. But changing the sequence of the actions, for example, cooking before mixing, will lead to a different and not tasty omelet. Or using different tools would not necessarily affect the action, yet current methods treat the entire scene as a whole, making it hard to generalize to different scenes with same actions. So the first paper I would like to present today is our CVPR paper, which demonstrates an object-centric approach for video transformers that extend transformer layers with a block that directly incorporate object representations. So intuitively, a human recognized this action would identify the hand, the coffee cup, and the coaster, and perceive the upward movement of the cup. And this highlights three important cues needed for recognizing actions. Where the objects are, how they do interact, and how do they move. And it seems intuitively clear that machine vision models should capture this reasoning structure. And indeed, this has been explored in the past. Recently, video transformers have been introduced as a very powerful video understanding models and have demonstrated great success in video understanding, yet existing video transformers do not explicitly model objects although objects can be essential for recognizing actions. In this paper, we demonstrated the value of an object-centric approach for video transformers. So our key observation is that self-attention can be applied jointly to object and spatiotemporal representation, and thus offering an elegant and straightforward mechanism to enhance spatiotemporal representations by the objects. We claim that self-attention in video transformer is a natural architecture to achieve this. The question is how? So in a standard transformer, each patch interacts with other patches. For example, at time t, the black temporal patch token attends to all blue patch tokens. Yet in Orbit, the orange object tokens, which correspond to class-agnostic detections, influence the spatiotemporal representation of the scenes. Thus, the black patch token attends to all blue patch tokens and the orange object tokens. And this allows the new patch representation to be informed by the objects. We show that integrating the Orbit block into video transformers lead to improved results on 4 video understanding tasks and 5 datasets. So let's sum up. In general, object-centric approaches have a stronger inductive bias, allowing us to generalize more effectively with less data. Additionally, the use of objects to better understand video scenes offer great potential. The main purpose was to demonstrate the potential utility of structured annotations for videos, and it was indeed useful. But obtaining structured annotations that contain information about the objects is tedious and time-consuming. It increases the training costs and reducing their scalability. However, what if only a small set of annotated still images is available? So to eliminate the need for full video annotations, we explored whether it is possible to incorporate the structure of images into video models, and surprised this seemed to be possible. I should also note that this work won the first place in the EGO4D CVPR 2022 Object State Localization Challenge. So in this work, we propose a learning framework called Structured Vid, or SVIT. SVIT demonstrates how utilizing information from a limited number of images that are available only during training can improve a video model. But what are our challenges to achieve this? So both images and videos contain structured information. And to leverage this structured information, we enrich a transformer model with a set of object tokens that can be used across the images and the videos. These tokens may be considered as a bridge between the image and the video domains. The object tokens are used to predict a particular instantiation of scene structure. We call it the hand object graph, which consists of hands and objects with their location as nodes and physical relations such as contact, no contact as edges. So our method is built on top of video transformer. First, we perform a small modification and transform it into a shared video and image transformer. We enrich a video transformer architecture with additional tokens that explicitly represent the objects. The object prompts are learned embeddings that we concatenate to the input patch tokens. The object tokens are the last representations of the object prompts. We expect each object token to represent an object in the scene. In training, each batch contains both videos and images. For image input, we predict the hand object graph using the object tokens. And for video input, we predict video classification using the patch tokens. And in inference, only the video frames are available. And now the learned object prompts enrich the patch tokens with structured information. Next, the enriched patch tokens are used to predict the video downstream task. So hopefully I've already convinced you of the benefit of object-centric models. We demonstrated how to take advantage of information that exists only partially in images for videos. And in light of this, I would suggest that we should model the world, objects and relations, rather than the data. But this work raises the question of whether it is possible to utilize even more information than objects, such as spatio-temporal scene-level information, for example, segmentation maps, depth maps, poses, and so on. So this is the purpose of our next work. This work is called Promptonomy Vit. This work has been done together with Ofir Avramovich, a master student, and Arik Shamir from Reichman University. So we are motivated to leverage scene-level information for downstream video tasks. As you are all aware, graphic engines can generate an enormous volume of labeled examples of scene-level data. However, it is not so easy to learn from synthetic data. In recent studies, it has been shown that synthetic data does not necessarily enhance action recognition, whether you're using pre-training data or fine-tuning data. In addition, learning from synthetic dataset is subject to domain gap issues. So the key observation we make is that vision transformers are capable of being naturally enhanced by synthetic sources. And we do that with prompt learning. The key idea of prompt learning methods is to augment the regular transformer input with a set of additional learnable parameters. More specifically, we add a set of task prompts that are dedicated to unique tasks. So prompt learning methods augment the regular transformer input with a set of additional learnable parameters, but keep it freezing the entire network. The purpose of this is to maximize the efficiency and leverage large foundation models that already have been pre-trained. Contrary to this, our work builds upon the transformer backbone, which has been trained for the primary task, and then adds new prompts for every task in its corresponding auxiliary task class. This utilizes transformer building blocks to provide different streams of information. So you can see here the framework and the model. We have a real data and synthetic data that have been processed by spatio-temporal patch tokens, similar to standard transformers. In parallel, we add task-specific prompts to learn from only the synthetic data. For instance, we can learn how to segment or how to predict depth maps. We refer to our prompt per task approach as promptonomy, since the prompts are intended to manage multiple prompts and capture inter-task structure. And with this design, it is possible to capture information shared among the synthetic scene task, as well as information shared between the synthetic scene task and the real video downstream task. So I hope I convince you why compositionality is an important aspect of intelligence and better machine vision models should require it. And I would like to finish or to end with a small presentation of, from my perspective, what are the challenges that remain in video understanding. So the first one is long-form video understanding. Unlike foundation models for language and images, longer videos still present a challenge today. The second one is video representation, and especially 3D representations and how they can help video understanding. And video and robotics, learning agents in multiple environments can benefit from learning from enormous video data. And my guess that it will be a significant progress in that aspect in the following year. That's all. Thank you.
Thank you, Roei. Any questions?
Hi, thank you. So my question is self-supervision not enough? Because you said you had one slide regarding the attention depending on, well, there was this paper from Meta, I believe, Dino, about emerging properties in attention models for video, I believe. So the question is just, is self-supervision not enough?
So right now, the biggest problem with self-supervision, it's not scale up. We see that as long as we feed more data, self-supervision has some barriers, some limit that it's not scale up, unlike big foundation models that we see that scale up. So taking Dino and keep training it on a lot of data has some barrier that we still not figure this out. Besides that, self-supervision gives us a very specific representations, more oriented toward captures and texture, more oriented toward texture and maybe low-level features, but not more high-level features. And what we are looking for right now is representations that we could use for reasoning or high-level complex tasks, like what we do with agents and in different multiple environments. That requires a different and more general approach than what we do today in self-supervised.
Okay, thank you.
Thank you. Any other questions? Okay, so I'll ask a quick question. I believe in the first two works you assumed that you have bounding boxes available. Did you consider training end-to-end also estimating these bounding boxes?
Yeah, so our second work, the SVIT, is doing that. It takes the objects as, I mean, the first work is using pre-trained models that knows how to give you the bounding boxes. And the second work try to show that I don't need a lot of annotations or bounding box annotations. I can try to detect it myself, and by doing this, I can also leverage the video models. That's exactly what the second work tried to solve.
Okay, thank you.
Thank you.
Okay, so even though we started late, we can thank Roei again.